in Britain as produced from nuclear power, a source of energy that's been used since 1956, when Her Majesty the Queen opened Calder Hall in Cumbria.
It is with pride that I now open Calder Hall, Britain's first atomic power station.
In a power station, heat is required to produce electricity. This can be provided by burning coal, by burning oil, or by splitting atoms of uranium in a reactor. Uranium is a naturally occurring ore found in many parts of the world. It consists mainly of two types of atoms, uranium-235 and uranium-238. The nucleus of an atom contains neutrons, which continuously bombard other atoms. When a neutron hits an atom of uranium-235, the atom splits and releases energy, mainly in the form of heat. 2 or 3 neutrons are thrown off as well, and each of these can split another atom of uranium-235. If this process continues, it's called a chain reaction, and the energy is liberated as heat. What hampers the chain reaction is that there is only 1 atom of uranium-235 to every 140 atoms of uranium-238. Only the uranium-235 atoms split and produce heat, so these are the ones we want. To produce a more efficient fuel, we must increase the number of uranium-235 atoms, and this process, known as enrichment, is carried out at Capenhurst. Capenhurst was built in the early 1950s to produce highly enriched uranium for defense purposes. This was achieved by a diffusion process, housed in what at the time was the largest building to be built in Europe. The plant consumed a great deal of electricity and was modified in 1965 to produce slightly enriched uranium to fuel the more advanced designs of nuclear power stations. The diffusion plant was finally closed down in 1982. And now, material for the Ministry of Defense is produced in this BNFL-owned plant using the new centrifuge enrichment process. Development of the centrifuge process began at Capenhurst in the early 1960s with the aim of producing a more efficient method of enrichment. The process exhibits a difference in weight between uranium-235 and uranium-238 atoms. Uranium, in a gaseous form, known as uranium fluoride, or HEX, is passed through rapidly spinning centrifuge machines operating on the same principle as a domestic spin dryer. A centrifuge machine consists of a rotor supported at the top and bottom by bearings and driven at very high speed by an electrical motor. The rotor is enclosed within a casing and operates under vacuum. Uranium hexafluoride gas is fed into the center of the machine. Because of centrifugal force, the heavier uranium-238 atoms move towards the wall of the rotor, and the lighter uranium-235 atoms concentrate around the axis. A countercurrent is set up within the rotor so that the gas enriched in uranium-235 atoms flows upwards to be collected by a scoop at the top, and the gas depleted in uranium-235 is collected at the bottom. A single machine can only achieve a small amount of enrichment, so a large number of them are joined together to form a cascade, which increases the amount of enrichment. European collaboration on the centrifuge process was brought about by an agreement between the Dutch, West German, and British governments. And in 1971, the international company Urenco was formed. British Nuclear Fuels owns 1/3 of the shares in Urenco and is the majority share in Urenco UK, a company formed to operate enrichment plants in Britain. The first plant to be built for Urenco UK was brought into operation at Capenhurst in 1977. In the plant, thousands of centrifuge machines mounted within blocks annually produce enough enriched uranium to fuel a power station capable of meeting the electrical demand of a large industrial city. And the added bonus, the machines consume only about 5% electricity required by the old-style diffusion plant. Centrifuge machines are designed to operate in years without maintenance, and the provision of high-quality machines is an essential part of the centrifuge project. Thousands of machines are required, and Capenhurst has a production line for their manufacture and assembly. Uranium hexafluoride is received at Capenhurst from chemical conversion plants worldwide, such as BNFL's Springfields works near Preston. At normal temperatures, hex is solid, so the container is loaded into a heating chest where the hex is converted back to a gas for transfer to the cascades of centrifuge machines. As the gas passes down the cascades from machine to machine, the separation and concentration of uranium-235 atoms is increased until the required amount of enrichment is achieved. The enriched hex, now ready for manufacture into nuclear fuel, is pumped into transit cylinders for dispatch to the customer's fuel manufacturing plant. The depleted hex is held in store at Capenhurst. Enriched hex, for use in Britain's advanced gas-cooled reactors, is sent to BNFL's Springfields works, where it's converted to a powder and pressed into pellets. The pellets are loaded into stainless steel cans and assembled inside graphite sleeves. Each of these clusters of fuel will produce the heat equivalent to burning 3,500 tons of coal. To meet the increased sales secured by Urenco from the nuclear power industry worldwide, a second and larger centrifuge plant came into operation at Capenhurst in 1983. Development of the centrifuge process is continuous, and other methods of enrichment are constantly being investigated. This will ensure that Capenhurst, with the capacity to produce every year the nuclear fuel equivalent of about 13 million tons of coal, will continue to be one of the world's most efficient plants for the enrichment of uranium.